Okay, so quickly going through the contents today, we'll be basically looking at two types of pre-stressed girder bridges. One of them is a solid infill deck type with TY beams. The in situ concrete will be poured between the gaps between the TY beams. And the second example is a traditional composite pre-stressed girder bridge with deck on top. We'll be using the W beams. W beams are recently have come up. It's one of the manufacturers, Banneker Concrete, have played a good role in this type of beams. Just a brief introduction on the concrete pre-stressed bridges. The structural behavior basically is the concrete beams are pre-tensioned with high tensile strength strands so as to produce only compressive stresses in the beams. And the deck, slab and the concrete beam act as composite. So we'll be looking at construction stage analysis with composite action in the presentation. Advantages of pre-stressed girder bridges, well, they can be used for any type of road bridges, rail bridges, footbridge, car parks, so any type of long span applications. We can use this type of pre-stressed concrete beams. The second advantage is ease of construction because the beams are precast, so easy to construct the bridge. Okay, so let's look at the first example, composite pre-stressed girder bridge with solid infill deck. Okay, so what I'll do is we will be taking an integral bridge with single span, and we have TY8 type of precast beam with solid infill slab. Okay, and we have got edge beams as well, TYE or TY edge beams. Okay. So let's see how to model this in the software. Okay. So I'm starting with a blank MIDAS screen at the moment. Okay. I'll quickly just draw some beams. Okay. We have covered the modeling process for integral bridges in our past webinars, so I'll be just going through quickly. Okay, so I'll just copy this member in the Y direction. Okay. Say 10 times. Apply and then draw the. So these are my main girders, pre-stressed girders, and then draw the grillage, transverse grillage members. And then simply, let's say, copy them. Okay, so simple creating and then copying them. Okay, say 10 times. Okay, so it's a 10-meter span, and we have got 10 such pre-stressed beams. Yeah. Now we'll draw the abutments very quickly, just using these end lines. And draw the abutments quickly. Yes, so we've got abutments out of these lines, and then we'll draw the piles. Just selecting few nodes here, and using these nodes we'll draw the piles. Okay, so that's the basic geometry for the integral bridge. No materials, no sections, no properties have been assigned to these elements. This is a grillage model. Now we'll focus on the materials and sections. So we'll go to properties, materials. So we can add a new material by selecting concrete from here and Eurocode and selecting a Eurocode material like C40 or C50, whatever it is. Okay. But to save time, I'll just import some materials from a previous model. So you see you can import materials from past projects. So I'll just select a past project, and all the materials I used in that project come up on the list here. Click OK, and that's it. So materials are selected. And then make sure sections. So similarly, sections I will import. Okay. Okay. All right. So all the sections I used in my previous project have come up. You can see all these beams sections. Okay. Now every element is assigned with the same section property because we didn't start with any assignment when we were drawing these elements. So I'll just make sure that these are assigned as piles, and then we have defined a thickness for the abutment, and just select all the transverse elements. So the transverse elements are selected, and drag and drop the transverse section. Okay. Okay. So except these longitudinal beams, all other sections are fine. Okay. So now I'll focus on how to model the composite pre-stressed sections, because that is the main topic today. So these longitudinal beams will be modeled as composite sections, composite pre-stressed beam sections. Okay. So how do we draw this type of sections? Well, we use a tool called section property calculator, tool section property calculator. So it comes up with a new drawing interface. This is a 2D drawing interface. I just select some units, Newton millimeters, for example, right? And then I go to model material. Because it's a composite section, I need to define two materials, one for the girder and one for the concrete slab. So add, and I select, just put a name, modulus of elasticity, let's say. All these values are just to initialize the section. You can define any material after assigning the section to the elements. And then in situ, concrete. Okay, so I've defined two materials. Now I'll define the section shape, the composite section, and quick generation. This is a new feature in the software MIDAS Civil 2015. The quick generation feature basically allows you to select pre-stressed concrete sections from a database, from the library. So we have got a library of different types of pre-stressed concrete sections. So we'll be using a TY beam for solid infill slab. So TY for solid slab. Okay, say I select this, and TY8. Okay, and then we'll define the slab dimensions, the concrete infill dimensions. Okay, and then width, something like this. Okay, and then we can export this section to the MIDAS section. Okay, and this type of a section is generated. Okay, similarly we can do the same thing for the other sections, the edge beam sections. So we define this time for edge beam, TYE for solid, TYE8. So there are two sections for left and right. So we'll define one for each edge beam. Same entries for the slab, and maybe something like this. Okay, and we can save this section as well, and you will get similar type of profile with an edge beam section. So I've already saved few of the sections that I'll be using. So I'll just close this section property calculator, and now I'll import those section into MIDAS Civil. So add, and my section is composite type, and it's a composite general section. Import from these files here. Okay, this is the same section which I generated, and I'll be also designing this section. So I'll put in some, because the software does not automatically know that which is the web or flange for pre-stressed concrete section. So we need to input some thickness for the web for shear checking, for shear resistance checks. So I put the input for the web here and give some name, and the second section, sorry, okay, let's say call it TYE8, and then another section, and okay. So I've saved all the required section. Now I'll assign them one by one. So I'll hide these transverse pile and plate elements. Okay, and I'll select the internal beams, and drag and drop simply the new sections which I generated. And drag and drop the edge beam section. Let's check. That's how you can see the sections look like. They're all composite sections now. Okay. So let's see how the completed model looks like. So I'll just open up the model which has been assigned with all the sections and properties. Okay. Right. So we have got the model here with all the abutments and all the transverse and longitudinal beams for the village. Okay. Now the next step is to define the pre-stressed tendon profiles in these sections. So just like we have a database of pre-stressed concrete sections, we also have a database of the tendon layouts from the precast beam manufacturer. So let me show you how to do that. So first of all, we define a material for the strand, for the steel strands. So that can be easily defined from materials. We have a database for different strand diameters. So we can select from the list. Type of material is steel, Eurocode, and select different types of strands from the Eurocode. Once we have done that, we then define the type of the tendon, whether it is pre-tension or post-tension tendon. So we use the tendon property feature, okay, and say it's pre-tension, post-tension, or external. Let's say pre-tension in this case. So we just give a name to the tendon. Material is selected, high tensile strength steel, And tendon area, so we select the strand diameter. There is again a list of the commonly used strand diameters. Select one of them and then define the relaxation loss coefficient, Eurocode, ordinary, low or hot rolled steel. Based on that, losses in the tendons will be calculated. You can see if you select post-tension tendon, you can also define anchorage slip and friction loss parameters. Okay, that's how we define the tendon property, and then we define the profiles. So for defining the profiles, I will just activate or isolate few girders. Okay, so I've grouped them here. We can create layers just like in AutoCAD. We can create groups here. Okay, so these are my internal beams, right? So I'm going to assign tendon profiles here. So we have a feature called pre-stressed concrete bridge tendon template. Okay, so once we are inside this dialog box, we can select based on a group. So select one of the groups here, right? So the top beam is selected. We can look at the cross-sectional view. That's how the shape looks like. You have the dimensions all noted down here. Okay. Now for this element or section, we can define the tendons using the auto generate function. Okay. Yeah. Okay, so either you can go to add and apply new tendons, just showing you some of the tendon profiles that are available. This type of tendons you can generate. It can be straight or parabolic. Okay. In our case, we'll be using straight tendons. Right. So let me just quickly go to straight the tendon option. Just quickly add up, bring on the section which I defined earlier. Okay. Okay, and that's the cross-sectional view. Now we can auto-generate tendons. So auto-generate and select which type of beam it is, right? So I selected TY beam, and it's a TY8 beam, and when I click OK, it will automatically enter all the tendon profiles. Okay, so all the tendon layout is automatically entered based on the precast beam manufacturer data. Now here, out of this, you can choose which tendons to keep, which ones to remove. You can select few tendons. You can say delete these tendons, or you can say select one of the tendons. Okay, move it up slightly. So move by these vertically or transversely. Okay. You can also choose to debond the tendons. So let's say I select one of the tendons, modify, and I can give a horizontal offset from begin and end of the beam. So let's say 2 meters and 2 meters, and okay. So that tendon is has been provided with a debonded length. And you can also save this tendon profile. So I can select the tendons and export them. So this will be saved as a tendon file, and if you want to add the same type of layout, the same debonded settings and everything, in a different model, in a different beam, you can use the import feature to get back the same tendons. Okay. So when I click on apply, the tendon gets applied to that beam. Similarly, I can do the same thing on the other beams. Apply, apply, and so on. So any number of beams, apply, and you can apply the tendons at different locations. So to view the tendon profiles that we have applied till now, okay, so I'll just highlight these. Okay, so you can see that the tendon profiles have been applied to different elements. From the top view also, if you see, some of the tendons are also offsetted, debonded. So you see this point here, the tendons which we debonded, they start from here, so 2 meters from the begin and end. So you can quickly create tendon profiles by just defining the type of section you are going to use in the model, and then quickly generating the profiles, debonding them, and deflecting them, or changing the shape of the tendon itself. Then the next step is to define reinforcement. You can, because the software can do the design of the sections, you can input reinforcement for both slab and for girder. So it will do a complete composite section check considering reinforcement and the pre-stressed tendons. So reinforcement can be defined in properties in the reinforcement option. Okay, you select say this particular section, and you can put in rebars. Say you can give a guideline, okay, something like this, and choose the diameter of the rebar you want, and then just draw along the guideline 4 rebars. And this is, since this is a slab, so part 2. Part 1 is the concrete girder. Okay, you can also add shear reinforcement, which are the links for the pre-stressed concrete girder. So in the shear reinforcement option, and just remove the guideline. Shear reinforcement option, you can put in your shear reinforcement pitch, spacing of the shear reinforcement, angle with respect to horizontal, longitudinal axis, and the number of legs. So 12 millimeter and number of legs, say 2, and click OK. You can also put in torsional resistance reinforcement for torsion resistance check. Again, the same way, transverse and longitudinal reinforcement which resists the torsion. You can input them here. Okay, so that's how the reinforcement and tendons are added in the pre-stressed concrete bridges. Now I'll quickly go over the construction stages, how to build up the construction stages in the model, and how to apply the pre-tension jacking force on the beams. So I'll first of all undisplay this tendon profile points, okay, and bring up the entire view. Now under the loads option, we have a tendon pre-stress option. You can simply select your load case name and the group name. You have created some load groups previously. Select which tendons you want to jack. So you select a list of tendons from this list, okay, and apply a jacking force from begin, end, or both ends, okay, and let's say 250 kilonewton and 250 kilonewton, and add. So 250 kilonewton jacking force will be applied to all the tendons, all the strands, and that's how pre-tension is applied. Now when the pre-tension will be applied will be decided by the construction stages. So we can tell the software that pre-tension will be applied when the concrete age is 7 days. That is a transfer of age at transfer is 7 days. Those type of things can be specified in construction stages. So how do we do that? How do we specify construction stages? We go to construction stage, define construction stage, and say create stage 1. So in stage 1 we'll have the substructure, abutments and piles. Okay. To generate construction stages for integral bridges, we have done a past webinar on integral bridges. You can check our YouTube channel for that. So I'm not going to details on how to create these groups and everything, but you can refer to our previous webinars on integral bridges. The focus is only on composite pre-stress application. So boundary conditions, all the soil springs should be there in the first stage, and then loads, self-weight from the very first day will start acting. Then stage 2, so in stage 2 we'll be applying all our pre-stress precast girders, TY8 girders. Okay. Now we can apply them at an age of 28 days, or if you want to be exact, we can change the age to 7 days, right, and apply pre-tension on the very first day. So let me just show you again. So what I do is, age is 7 days here, select all the precast beams, add them, and then boundary conditions. Since in the first stage the precast girders will be simply supported on the abutments, and then later on when the concrete is poured, everything will become composite and integral. So that's why in the first stage, when the precast girders are first installed, we apply moment releases, that is pinned connections at the ends. So moment releases are applied as boundary conditions, and then for the loads we'll apply wet concrete load, which is the slab UDL, the weight of the infill concrete, which has not become composite, but the wet concrete load will still be acting on the precast girders. And the pre-tension jacking force will also be applied from the very first day. The very first day means concrete age is 7 days as per this setting. Okay, so that's how the stage 2 is built. And then finally stage 3, this is having 10,000 days to take care of the long-term effects. So in stage 3, which is the last stage, we activate our transverse grillage members and edge beams, because now the slab has become composite, and the transverse grillage members will also come into picture. And boundary conditions will remove moment release, so pinned conditions are removed. Everything is integral now, and finally surfacing is applied on the 21st day when the slab attains an age of 28 days. Okay, and we also need to separate out the composite sections for construction stage, because what happens now is the software treats one element as a complete composite section. So in order to differentiate that, in stage 1 software should use only precast beam stiffness, and in stage 2 the software should use both precast beam and the slab stiffness. In order to make that demarcation, we use composite section for construction stage. So inside this option, we tell the software that, say, stage 2, select beam section, okay, and tell the software that, okay, part 1, which is pre-stressed concrete girder, will have a material called precast girder and will be activated or installed on stage 2. Age will be 7 days. That's the age from where the pre-stress was applied, and creep and shrinkage will also start acting. And part 2, which is concrete slab, material will be slab, and stage will be stage 3. So that's how the software knows that in stage 3 it will add both the slab and precast beam stiffness. And then age of a slab, when the slab first becomes composite, the age is 7 days. Okay. Now there can be a situation, especially near the supports, near the abutments, the slab may be cracked. may have some tensile stresses. So in order to take care of that kind of situation where the slab is supposed to be cracked, we can modify the stiffness of the slab. Okay, so for every part 1 and part 2, you can modify the stiffness. So you've got some slab stiffness, area of the slab, and moment of inertia and centroid, everything is there for the slab. Now you can put a stiffness scale factor, put area moment of inertia 0, 0, 0, which means that the slab is cracked, there is only beam sections. So you can do such type of modifications as well. Go for cracked and uncracked section. Like in this case, we have defined infill TY8 infill and TY8 infill cracked section for the end beams. You can see these highlighted zones. Okay, that's how you can take care of cracking of the slab in the analysis. Okay, so let's look at how this construction staging looks like. So I'll just open up the full model now. Okay. All right, so that's the full construction stage model. Let's see, in stage 1 we have only abutments and piles. We have got some soil springs as well. The software has got the automated method for generating soil springs from raw soil data, which we have covered in previous integral bridge webinars too. Stage 1, stage 2, we've got only precast beams, and we've got beam end releases. So we've got pin connection. See, there are these dots, these symbols at the end, they represent pin connection. And in stage 3, we've got the entire grillage activated with the composite action. Okay, now let's look at the results. This model is already analyzed, and we'll quickly look at the results for construction stages. So stage 1, let's look at stage 2 onwards, because that's when the precast beams are activated. Beam diagrams. Okay, so let's see dead load. Apply. So because it's simply supported, we have got bending moment, no hogging moments, only sagging moments are there. Okay, we can look at tendon primary effects. See, because the structure will be indeterminate later on, we may have secondary effects. So if you go to stage 3, we can look at pre-stress primary as well as pre-stress secondary effects. Okay, so pre-stress secondary effects in the piles and also on the beams. Also, we'll have creep primary and creep secondary effects, shrinkage secondary effects. We have defined time-dependent material properties for both beams, precast beam and the concrete slab. Okay, so the way you do that in the software is very simple: creep, shrinkage, material function, precast, one for the precast beam. We define the characteristic strength, relative humidity, and then it will calculate the creep coefficient and shrinkage strain curve required for the analysis. And similarly for compressive strength, we define just a strength, mean strength of concrete, and it will create a strength versus time graph, and both short-term and long-term elasticity will be considered automatically based on the duration of each construction stage. So if you remember, we put in some duration for construction stage, some age of concrete, and the graph will follow that particular age. So creep and shrinkage effects can be visualized here. Also, if you're interested in stresses for designing composite section, we are mostly interested in the stresses. So we can look at stresses. Let's say summation of all effects. If I'm interested in looking at stresses in the bottom fiber of pre-stressed girder, so I select part 1, which is pre-stressed girder. Bottom fiber is part 4 as per this figure, and apply. So this gives me a stress distribution. The legend shows negative values means compression. And if I go to part 2, which is a concrete slab, and maybe look at top of the slab, which is point number 1 as per this figure, apply. So see, I've specified a cracked section at the end, so there is no stress at the ends, whereas in the middle you have some stresses. You have some tensile stresses over here, and rest of the region is compressive in the middle for the slab. Now, one of the other important features for pre-stressed bridges is to look at losses in tendons. So the software also generates tendon losses. If I look at tendon loss graph, because we have defined so many strands, we can select which strand we want to look at and browse through different stages. So stage 1, we have only the abutment, so no strand. Stage 2, so we applied roughly 210 kilonewton force, and due to immediate shortening, the force was reduced to somewhat 170 kilonewtons. And then stage 3, there is further reduction due to time dependent losses. You see the force variation. This distance is actually the length of the beam, the length of the tendon basically, and the y-axis is the tendon force. So you can animate it just to see how forces are varying in the tendons. Another important result is the tendon loss that you can obtain in a table format. So basically you can see each and every loss coming out from immediate effects, creep and shrinkage or relaxation effects. See, that's the tendon number 1, stress after immediate shortening, stress after creep and shrinkage and relaxation, all those stresses you can see, and the effective stress ratio final upon initial stress. Okay. This can be useful in determining the tendon jacking force. Then after all these results, we come to the design now, where we can actually design the all these sections, pre-stressed concrete sections. Okay, so I'll just remove the results here. So for design, we select Eurocode. We support Eurocode design at the moment. For composite pre-stressed sections, British National Annex can be selected. The pre-stressed steel types is a strand. Then what type of checks you want to do, bending, shear, torsion, and stress checks, crack control. It also does decompression checks. And then we define the design material for checking. So what type of concrete grade you want to use, rebars you want to use, slab materials, slab grade, rebar for the slab. Okay, and then serviceability combination types. So because the Eurocode, we have 3 types of SLS cases: quasi-permanent, frequent, and characteristic. So based on which load combination you want to enter in which type, you just put them here. And also shear interface, the interface between the composite slab and the concrete girder. You can put some interface data like rough surface, rough interface for calculating interface shear. You can put the reinforcement area and the strength of the reinforcement as well. And then exposure class for carrying out the crack width checks. So you select the beams and define what exposure class of concrete it is. Okay, and then after the design, you get result tables for flexure strength. For example, you get a table which basically shows you the applied moment, moment of resistance, and the ratio of checking. If anything is failing for any element, that element will be marked in red, and you know that it's failing. And you can then look at the report, the full calculation report on why it is failing by clicking on Excel report. So just to show you how the Excel report looks like, you get a report like this, okay, with all code clauses from the relevant clauses from the code, okay, figure for the section you're trying to design with all the tendon locations, and again clauses from the code and tendon profile information, ultimate moment resistance checks, calculation of neutral axis. So the entire step-by-step calculation is you can always reference from the design report, okay, which is generated by the software in Excel. Since it is generated in Excel, you can also type in your own code here and post-process these results further. Okay, so shear resistance checks, okay, decompression checks, again code clauses are there. Okay, the software does tendon stress limit check, so checking tensile stress for pre-stressed strands if the tensile stress exceeds the allowable stress limits. Then you can also look at result diagrams. This is a very good feature to quickly check what percentage of the beams are crossing the safety line. So let's say for bending resistance, apply. Okay, so I've only designed for the central beams. Okay, so you can see the shaded part, the solid shaded part represents the applied moments, and the dashed lines, they represent the moment resistance. So that's more than the applied moment, so it's fine. Same thing you can check for stresses on the for construction stages. At the bottom fiber, apply. You get again dashed lines and some shaded lines. Shaded lines here are more than, shaded values are more than the dashed lines, so that means for the stress limitation checks it is it's failing. Okay, so you can make out these inferences directly from the result diagrams. Okay, so just quickly moving on to the next example, which is the W beams with slab on top. Okay, the method of modeling is a two-span integral bridge. Method of modeling is similar to what we saw for the single-span integral bridge. Here also the pre-stressed concrete girders will be first simply supported on the abutments and the pier, central pier, and then when the slab is poured, it becomes all composite and integral. Okay, so going back to the model. Okay, so that's the model of the W beams. To model the tendons for W beams, you just select, say I activate W beams here. Okay, you select a few elements and then you go to structure, tendon template, and use auto generation function. W11 is automatically detected based on the dimensions here, and you click OK. And automatically you have got all the tendons in from the library. Now up to you, you can delete some of the tendons, you can debond them by selecting some tendons and or export and save a particular layout and use them for later on for subsequent analysis. Okay, so that's the procedure is same. Construction stages, just going through briefly on the construction stages. Stage 1, you've got these precast beams only. Stage 2, wet concrete is applied, so you'll find the wet concrete load is applied in stage 2, and stage 3 everything becomes composite and integral. Okay, so let's look at the results for this analysis too. So let's see stage 2 forces. Okay, so that's summation effects. If I look at dead load, so it's simply supported dead loads, tendon primary or pre-stressed primary effects. Okay, more or less uniform type of moment because eccentricity is uniform if you take the total centroid of all the tendons. And creep in stage 3, you will also see moments due to creep secondary, creep because the structure becomes indeterminate. So creep secondary effect moments will start coming into picture. So you have creep secondary moment and also tendon secondary moments. Okay. Again, the design to design this type of section, we again use the same tool, Eurocode 2 British National Annex, and select what checks we want to do, and then we can put in some rebars as well, like I have done in this case. Selected reinforcement, put some reinforcement in. There are small dots you can see, the other reinforcement entered, and then finally after report generation you get a report similar to this with the reinforcement layout shown and with the tendon layout and all step-by-step calculation. Okay, so pretty much it does the pre-stressed concrete design for you, and you can always change the tendon profiles, okay, and redesign to come up with a more optimized tendon layout. Okay, so these are the two examples that I wanted to show you today, and that basically sums up the features that we have for the composite pre-stressed design of the composite pre-stressed girder type of bridges for both solid solid infill and as well as slab on top type of sections. So we have a whole library of sections which you can bring in, and also the tendon profiles you can automatically bring in from the library. Okay, so just to pause here, I've got a few questions I would like to answer. One of our attendees has asked, can the tendon template be used to edit the tendon subsequently? Yeah, as I said, you can save the tendon template input as a tendon file, export it, and then import it back and edit, and then apply it again. Okay. And another question is how the top slab is connected to PC beams. Well, it is because this is the composite section, it's assumed a rigid connection. Okay, but for designing purposes we do check for the interface shear between the slab and the PC beams. Okay, so now to close up the session, I'll move on to the BIM part, Revit civil, Revit structure and MIDAS civil interaction. Okay, so we have we can export a section from MIDAS civil into Revit through IFC file format, and we can also export a section out of Revit and send it back to MIDAS civil. Okay, so I'll show you both these processes. I'll take two examples, one of general structure in Revit and like a building shown here, which has steel and concrete and every other different types of sections. And I'll take one example for the for a bridge solely constructed in MIDAS civil and then brought into brought into Autodesk Revit. Okay, the similar type of interface works with Tekla structures. So I'm not using Tekla structure right now. So exactly the same interface is there with Tekla structure. Okay, so we've got an export to IFC file feature. Export to IFC file basically creates text file of IFC file format, we call it. Okay, and you can save it. Maybe just give it a different name. Save it. Okay, so you get an a file format like this, an IFC file format. Then this is for models which you generate from scratch inside MIDAS. If you want to use these models for other architectural drawings or anything, then you can use this feature, IFC file feature. I'll open up new project in Revit. So this is Autodesk Revit interface. Okay, and just go to open IFC file and just select the IFC file that I selected. Okay. Yes. So it's now importing the files. Okay. Till then, I'll just answer a few more questions that have been raised here. One of the questions is related to fiberglass decks. If MIDAS can model fiberglass decks, well, as long as you know the properties of the the material you're going to assign. You can define any material in the software. So normally for glass, we'll go for orthotropic material, and we use plate elements for the deck, so not composite sections. What we use grillage model in today's example, but instead of grillage model, we model the plate slab as plate elements for such type of user-defined sections. Okay, so just turn on. Okay. Okay, so just showing you some 2D views here for the bridge that we modeled here. Since it's a meshed model, so you will get divisions in Revit too. Okay, so to control the size of the mesh, you have to control, because this is a mesh you're bringing in into Revit from Civil. And also you can look at the 3D format. You can just show all the analytical views. Okay. 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 Okay, so that's the 3D view of the same model, analytical model. Okay, so all the elements and the divisions are there. You can see. Okay, and so this is how you can bring in any type of finite element. It can be a plate model, it can be a grillage model, any type of model you can bring in directly into MIDAS, into Revit through IFC file format. And the other way around, if you have an existing Revit model, then you can bring those Revit model in the Revit structure model into MIDAS Civil. So for this, I'll just take a general structure as an example. Okay, so I'll just close this. Okay. Okay, so I'll take this structure as an example. Okay, it can be any type of structure. I just chose this one because it has got different types of sections in it, steel and concrete, both materials. We have got an add-in here. In Revit you have add-in external tools. You can send the this model to MIDAS Civil. Okay, updates after running the analysis in MIDAS Civil, you can update some of the sections and update them in Revit as well using update model option. So I'll show you the send model feature. So when you're sending it, you can adjust the mesh size because it's got a slab on it on all the floors, so you can adjust what size of mesh you want for the finite element slab, and yeah, and then you can send it into the software. Okay, so yes. Okay, and continue. See, it will give you a message showing which sections are linked to which particular section in Civil, in MIDAS Civil. You can also put your own rules here. So it will identify all the British standard sections. Okay, when you continue. Okay, so it will calculate the geometry and search for the good connections between columns and slabs, beams and columns. Okay, and in the software, you just open up new project. Okay. Okay, so while it is calculating on the mesh size, I'll just answer a few more questions here. One of the questions is, can the models be exported from MIDAS Civil into general.dwg files? Yes, you can always export the model into DWG files. Let me just show you. So you've got, say, the similar model. You can export to AutoCAD DXF. Okay, it's saved as a DXF file, but it's the same file format can be changed in AutoCAD. So export model to DXF, you can save center lines, plus you can save the shape of the model. So you can save the shape of all your sections that you've used in the model, okay? And you can put in your thicknesses and plate thicknesses, and when you look at the AutoCAD drawing, it will reflect the correct shape of the model. Okay? And then you can convert it into MicroStation as well. Inside AutoCAD, you can do that, save it as DGN files. Okay, so just import. Okay, so got the file now. Send it. Okay, so we've got the model generated. You see all the plates, the slab has been meshed. Okay, you can, I'll just remove the nodes from the view. So the slab has been meshed and all the sections, all the steel sections are in. If you have put in any loads in Revit, you can also bring in those loads like live loads and some pressure loads were inputted in Revit. You can bring in those loads too. Okay, so loads are also imported. Pin connections between beams and columns. See, columns are all pinned, top and bottom are pinned. Even those pin connections are brought in. Then supports over here. Okay, they have been also defined. Okay, and different thicknesses for slabs and walls. Different types of material sections. Okay, so these type of sections were there in the library of Revit, and they are brought into MIDAS 7. Okay, so that basically covers the BIM part of it, of the presentation. So you can see that you can import from Revit as well as send a completed model back to Revit if you're drawing it from scratch inside the software. Okay. Similarly, if you import something from Revit, if you change the sections, you can also update the models in Revit using the update model feature. Okay, so that basically brings us end of the presentation. The presentation will be, the video will be available on YouTube shortly. So we'll be sending out links for that. If you need any free bespoke demonstration, we do customized webinars on different topics. You can visit your office as well for customized trainings. If you need anything, if you have any questions or need any kind of demonstrations, do contact us. Our details are shown here, or email us at uksupport@midasuser.com. For our past webinars, you can log into the YouTube channel Midas UK. Search for Midas UK on YouTube, and you'll get all our past webinars up there. Okay. So with that, I'll end the presentation and end the webinar. Thank you for joining, and take care.